the grand theater of our solar system, where worlds spin in silence and light dances across unfathomable distances, there exists a planet that has captivated humanity's imagination for millennia. We gaze upward at the evening sky and see her there, brilliant and unwavering, a point of light so bright it casts shadows on Earth. The ancients called her the morning star, the evening star, never realizing they observed the same celestial body at different times. They named her Venus, after the goddess of beauty and love, for surely something so radiant in the heavens must embody grace itself. But beauty, as we have learned through countless human experiences, often conceals complexity. The most alluring surfaces can hide the most turbulent depths. What appears serene from a distance may roil with chaos up close. And Venus, our nearest planetary neighbor, our sister world in size and composition, holds secrets that challenge everything we thought we understood about how planets should behave. For centuries, Venus remained an enigma wrapped in brilliance. Through even the most powerful telescopes, astronomers could discern nothing of her surface. No features, no continents, no seas of the kind that mark our Earth. Just an unbroken veil of white and yellow clouds that reflected sunlight with such intensity that Venus became the third brightest object in our sky after the sun and moon. This featureless face fueled endless speculation. What lay beneath those clouds? Was Venus a world of oceans, as some imagined? A tropical paradise warmed by proximity to the sun? Or something else entirely? The truth, when we finally pierced that veil, proved far stranger than any speculation. Venus is not merely different from Earth. Venus is wrong in ways that defy our understanding of planetary physics. The images we have captured, the data we have gathered, the measurements we have taken all point to a world that operates according to rules that seem to contradict the fundamental principles governing the other planets in our solar system. Consider this: Venus rotates backwards. While every other major planet in our solar system spins in the same direction they orbit the Sun, Venus turns the opposite way. If you could stand on the surface of Venus and survive the conditions there, you would witness the Sun rising in the west and setting in the east. This retrograde rotation is so slow that a single day on Venus, one complete rotation on its axis, takes 243 Earth days. Yet Venus completes its orbit around the Sun in only 225 Earth days. This means that a day on Venus is longer than a year on Venus. A single sunrise to the next sunrise takes 116 Earth days, making the Venusian day-night cycle one of the longest in our solar system. How does the planet end up rotating backwards? The most common explanation involves a catastrophic collision early in Venus's history, an impact so massive it literally knocked the planet over, flipping its rotational axis. But this explanation raises more questions than it answers. Such a collision would have been extraordinarily violent, potentially melting the entire planet, vaporizing any atmosphere, and leaving debris that should still be detectable today. Yet we see no evidence of such a cataclysm. No unusual distribution of mass within the planet, no debris field, no chemical signatures that would indicate Venus was once melted and reformed. Other theories suggest that gravitational interactions with the Sun, combined with Venus's thick atmosphere, could have gradually slowed and then reversed the planet's rotation over billions of years. But the mathematics of this process remain uncertain, and no other planet in our solar system has undergone such a transformation. Venus stands alone in its backward spin, a cosmic anomaly that defies simple explanation. But the strangeness of Venus extends far beyond its rotation. When our first spacecraft finally penetrated those impenetrable clouds in the 1970s, they found a world of such extreme hostility that it redefined our understanding of what a planetary surface could be like. The Soviet Venera probes, those brave mechanical explorers, descended through an atmosphere so dense it crushed them like tin cans. Those that survived the descent landed on a surface where the temperature exceeds 900 degrees Fahrenheit, hot enough to melt lead, hot enough to make zinc flow like water. This is not the gentle warmth of a planet closer to the Sunday. This is a runaway greenhouse effect of such magnitude that it has transformed Venus into the hottest planet in our solar system, hotter even than Mercury, despite being nearly twice as far from the Sunday. The atmosphere, composed primarily of carbon dioxide, with clouds of sulfuric acid, traps heat with ruthless efficiency. Pressure at the surface reaches 92 times that of Earth's atmosphere at sea level, equivalent to being 3,000 feet underwater in Earth's oceans. The images transmitted back by those Venera landers, before the extreme conditions destroyed them within hours, showed a landscape of flat volcanic plains stretching to the horizon, rocks scattered across the surface, a sky glowing orange from the thick atmosphere above. These were the first, and for many years, the only photographs ever taken from the surface of another planet. They revealed a world that was alien in every sense, a place where the very concept of habitability seemed laughable. And yet, Venus was not always this way. Evidence suggests that billions of years ago, Venus may have been far more similar to Earth than it is today. Some models indicate that Venus could have once possessed liquid water on its surface, possibly even oceans that persisted for billions of years. The planet's proximity to the Sun would have provided abundant energy. Its size and composition were nearly identical to Earth's, and during the early solar system, conditions might have been just right for Venus to harbor a temperate climate. What happened? How did a planet that may have been Earth's twin transform into a hellish furnace? The answer appears to lie in a delicate balance that Venus lost and Earth maintained. At some point in Venus's past, perhaps due to increased solar radiation as our sun grew brighter over time, perhaps due to massive volcanic eruptions that pumped greenhouse gases into the atmosphere, perhaps due to the loss of water that would have helped regulate temperature, Venus crossed a threshold. The planet began to warm. As it warmed, any water on the surface evaporated. Water vapor is itself a powerful greenhouse gas. So this evaporation caused further warming, which caused more evaporation in an accelerating feedback loop. Eventually, the water vapor rose high enough in the atmosphere that ultraviolet radiation from the sun could break it apart into hydrogen and oxygen. The lightweight hydrogen escaped to space, lost forever. The oxygen reacted with rocks on the surface, incorporating into minerals. Venus's water, the substance that might have kept the planet temperate, vanished into space in stone. What remained was carbon dioxide, released from volcanic activity and unable to be absorbed back into the planet without liquid water to facilitate the process. The atmosphere thickened, the temperature soared, and Venus became the inferno we see today. This process, this runaway greenhouse effect, serves as a dire warning for Earth. Our planet sits just far enough from the Sun to maintain the delicate balance that Venus lost. But that balance is not guaranteed to persist. If Earth's atmosphere accumulates too much carbon dioxide, if our temperature rises too far, we could theoretically trigger the same kind of feedback loop that doomed Venus. This is not speculation or alarmism. This is planetary physics, demonstrated in our own solar system. But Venus continues to surprise us, continues to reveal phenomena that challenge our models and assumptions. In 2006, the European Space Agency's Venus Express spacecraft began studying the planet in unprecedented detail. Using instruments that could pierce the cloud cover, scientists mapped the surface, studied the atmosphere, and monitored the planet's behavior over years. What they found defied explanation. Venus's atmosphere super-rotates. While the planet itself turns slowly backwards, the atmosphere whips around the planet at speeds exceeding 200 miles per hour at the cloud tops, circling the entire planet in just 4 Earth days. This means the atmosphere rotates 60 times faster than the planet beneath it. Imagine Earth's atmosphere circling the globe every 7 hours, while the planet itself took 24 days to complete one rotation. The forces required to maintain such a phenomenon are immense, and scientists still debate exactly how this superrotation is sustained. The clouds themselves form patterns unlike anything seen elsewhere in the solar system. At Venus's poles, the fast-moving atmosphere creates enormous vortexes, swirling storms larger than continents that persist for years. These polar vortexes have a strange, almost geometric structure, sometimes forming shapes that look almost like eyes staring out from the planet. The clouds race from the equator toward the poles, pile up, and then sink, creating convection patterns on a planetary scale. Within these clouds, we have detected phenomena that seem impossible. Lightning flickers through the sulfuric acid clouds, though the electrical discharges appear different from Earth's lightning, possibly created by different mechanisms. The clouds contain droplets of sulfuric acid concentrated enough to dissolve metal, yet they never reach the surface, evaporating in the intense heat of the lower atmosphere before they can rain down. And within certain layers of the clouds, at altitudes where the temperature and pressure become more Earth-like, we have detected chemical anomalies that some scientists interpret as potential biosignatures. In 2020, a team of scientists announced the detection of phosphine in Venus's atmosphere. Phosphine is a gas that on Earth is primarily produced by biological processes or industrial activity. There are very few known ways to produce phosphine through purely geological or chemical processes, especially in the quantities detected. The announcement sparked intense debate and scrutiny. Some scientists questioned the detection itself, arguing that the signal could be misinterpreted, or that interference from other chemicals could create a false positive. Others accepted the detection, but proposed alternative explanations, rare chemical reactions that might occur in Venus's unusual atmospheric chemistry. But a subset of scientists suggested something more provocative. If the phosphine detection is real, and if we cannot explain it through known non-biological processes, could it indicate life? Not life on Venus's surface, which is utterly inhospitable, but life in the clouds, in that narrow altitude range where temperatures and pressures resemble Earth's surface? Could microorganisms, perhaps descendants of life that evolved when Venus was more temperate, have adapted to an aerial existence, floating in the clouds, reproducing and metabolizing in droplets of acid? This hypothesis stretches our understanding of biology's limits. Life in concentrated sulfuric acid seems absurd, yet we know from Earth that extremophile organisms can survive in environments once thought uninhabitable. We have found life in boiling hot springs, in acid lakes, in the dry valleys of Antarctica, in salt crystals millions of years old, kilometers beneath the ocean floor. Life, once it gains a foothold, proves remarkably resilient and adaptable. Could it have adapted to Venus's clouds? The question remains open, fiercely debated, and critically important. If life exists on Venus, it would revolutionize our understanding of biology's potential. It would suggest that life can arise and persist in environments far more extreme than we imagined. It would mean that our solar system contains at least 2 planets that independently developed life, which would in turn suggest that life throughout the universe is far more common than we dared hope. But even without life, Venus's clouds hold mysteries that challenge our physics. Recent observations have revealed that the upper atmosphere of Venus is losing oxygen at a rate that cannot be easily explained. Something is stripping oxygen from the planet at an accelerating pace. The solar wind, that stream of charged particles flowing from the sun, certainly plays a role, but the rate of loss exceeds what models predict. What else is happening? Are there chemical processes we do not understand? Is there some interaction between Venus's atmosphere and magnetic field, or lack thereof, that we have not accounted for? Venus lacks a global magnetic field, unlike Earth. Our planet's magnetic field, generated by the churning of molten iron in our core, shields us from the solar wind and helps retain our atmosphere. Venus's core may have solidified, or perhaps the planet's slow rotation prevents the dynamo effect that would generate a field. Without this protection, the solar wind interacts directly with Venus's upper atmosphere, stripping away particles over time. Over billions of years, this process could have contributed to the loss of Venus's water as hydrogen escaped to space. Yet even this explanation feels incomplete. Venus's atmosphere is so massive, so dense, that even billions of years of solar wind should not have depleted it as much as observations suggest. Something else, some additional process or event, must have played a role in shaping Venus into the world we see today. The surface of Venus, hidden beneath those clouds, reveals its own collection of mysteries. Radar mapping from orbit has allowed us to peer through the atmosphere and create detailed topographical maps. What we see is a world dominated by volcanism on a scale that dwarfs Earth's volcanic activity. Vast lava plains cover most of the planet. Shield volcanoes, some larger than any on Earth, rise from these plains. Volcanic features called coronae, circular structures hundreds of miles across where magma has pushed up the crust, dot the landscape. But here is the strange part. Venus's surface appears remarkably young. Crater counting, a technique that estimates surface age by the number and size of impact craters, suggests that Venus's entire surface is between 300 and 600 million years old. This is very young in geological terms. Earth's oldest rocks are over 4 billion years old. Something resurfaced Venus relatively recently, erasing all older craters and features. The most likely explanation is a global resurfacing event, a period of catastrophic volcanic activity that covered the entire planet with fresh lava. But why would this happen? What triggered such planet-wide volcanism? And did it happen once? Or does Venus periodically resurface itself every few hundred million years? If the latter, we have no good explanation for what would cause such regular cataclysms. Some scientists propose that Venus's interior heat builds up over time, unable to escape efficiently through plate tectonics, like Earth's heat does. Eventually, the pressure becomes too great, and the entire planet's crust breaks apart, allowing massive volumes of lava to flood the surface before the crust reforms and the cycle begins again. Others suggest that Venus does have some form of plate tectonics, just fundamentally different from Earth's, operating in episodic bursts, rather than the continuous motion we see on our planet. The question matters because understanding Venus's geology could help us understand how rocky planets evolve. Earth has plate tectonics, a system where the crust is broken into plates that slowly move, collide, and subduct. This system recycles material between the surface and interior, regulates atmospheric chemistry, and may be essential for maintaining conditions suitable for life. Venus appears to lack this system, or to operate under a completely different paradigm. Why the difference? Both planets are similar in size and composition. What factor or factors caused Earth and Venus to develop such different geological systems? One possibility involves water. Earth's oceans not only make plate tectonics possible by lubricating the boundaries between plates, but also help regulate the planet's temperature and chemistry. Without liquid water, Venus's crust may have become too stiff, too rigid, for plate tectonics to operate. Instead, heat builds up until the pressure forces a catastrophic release. If this hypothesis is correct, it underscores once again how critical water is for maintaining a stable, habitable planet. Recent missions to Venus have provided tantalizing glimpses of ongoing volcanic activity. The Venus Express spacecraft detected temperature variations on the surface consistent with fresh lava flows. The sulfur dioxide concentration in the upper atmosphere fluctuates in ways that suggest volcanic eruptions injecting new gas into the air. These observations hint that Venus is not a dead world, but a geologically active planet where volcanoes may erupt even today. Imagine standing on Venus's surface, if such a thing were possible. The sky above you glows orange, the thick atmosphere scattering light in ways that eliminate shadows. The air is so dense it behaves almost like a fluid, and you can barely see more than a few hundred feet through the haze. The ground beneath you is flat volcanic rock, basalt that flowed as liquid stone and cooled into solid plains. In the distance, you might see mountains rising, or the gentle slope of a shield volcano, or perhaps one of the enigmatic coronae, a circular ridge system that hints at magma chambers beneath. The temperature is unbearable, hot enough that the rocks themselves glow faintly in the infrared. The pressure crushes down on you with the weight of an ocean. Sulfuric acid particles drift on the wind, and the atmosphere is so thick that even the strongest winds move slowly, pushing through the heavy air. This is a world utterly hostile to human life, and yet it is Earth's closest planetary neighbor, a world that might once have been almost identical to our own. The divergent evolution of Earth and Venus represents one of the most profound questions in planetary science. Why did two planets, born from the same cloud of dust and gas, located in the same solar system, with nearly identical size and composition, develop into such radically different worlds? The answer holds implications not just for understanding our solar system, but for evaluating the habitability of planets around other stars. As we discover thousands of exoplanets orbiting distant suns, we find many that fall into the category of Venus analogs, rocky planets similar in size to Venus or Earth, orbiting at distances where they receive similar amounts of stellar radiation. Are these planets doomed to become hellish worlds like Venus? Or could some maintain Earth-like conditions? The factors that determine this outcome, the variables that tip the balance between temperate and inferno, remain poorly understood. Venus is our laboratory for understanding these processes, a nearby example of planetary evolution gone wrong, or at least gone differently. The exploration of Venus has been a story of triumph and tragedy, of remarkable achievements and heartbreaking failures. Every mission to Venus must contend with conditions that destroy spacecraft with ruthless efficiency. The heat melts electronics, the pressure crushes structures, the acid corrodes materials, and the thick atmosphere makes landing a harrowing ordeal. Yet humanity has persisted in sending probes to this hostile world, driven by the knowledge that understanding Venus is essential to understanding planets in general. The Soviet Union, during the height of the space race, mounted an extraordinary campaign to explore Venus. Between 1961 and 1984, they launched dozens of Venera probes toward the planet. The early missions failed spectacularly. Venera 1 lost contact during its journey. Venera 2's instruments failed before arrival. Venera 3 became the first spacecraft to reach another planet's surface when it crashed into Venus in 1966, but it transmitted no data during descent. The Soviets learned, adapted, and tried again. Venera 4, in 1967, successfully transmitted data during its descent through Venus's atmosphere, revealing for the first time the true nature of the planet's atmospheric composition and pressure. The probe was crushed by the pressure before reaching the surface, but it had provided invaluable information. Subsequent Veneras were built stronger, tougher, designed to survive the descent, and operate on the surface for at least a brief time. Venera 7, in 1970, became the first spacecraft to successfully land on another planet and transmit data from the surface. It survived for 23 minutes in the inferno before succumbing to the heat. Venera 8 followed in 1972, lasting 50 minutes. Each mission pushed the boundaries of engineering. Each probe was a masterpiece of robust design, built to withstand conditions that would destroy any ordinary spacecraft within seconds. The greatest triumph came with Venera 9 and 10 in 1975. These probes not only landed successfully, but carried cameras that captured the first photographs from the surface of another planet. The images they returned showed a landscape of flat rocks stretching to the horizon under an orange sky. The detail was remarkable, considering the conditions. You could see individual rocks, their textures, the way they lay scattered across the volcanic plain. These images proved that the surface of Venus was not molten, as some had theorized, but solid, though baked by temperatures that would melt lead. Venera 13 and 14, launched in 1981, achieved even more. They returned color photographs that showed the true appearance of Venus's surface. The orange glow, the flat basaltic rocks, the alien landscape under immense pressure. Venera 13 survived for 127 minutes, a record that stands to this day. The probe analyzed rock samples, measured the atmosphere, recorded sounds, and transmitted all this data back to Earth before finally failing in the extreme heat. These Soviet achievements represented some of the most challenging robotic exploration missions ever attempted. The engineering required to build spacecraft that could survive even briefly on Venus's surface was extraordinary. The probes had to be cooled before landing, insulated against the heat, armored against the pressure, and sealed against the corrosive atmosphere. Even with all these precautions, they could only operate for a few hours at most before the conditions destroyed them. The United States took a different approach to Venus exploration, focusing primarily on orbital missions and atmospheric probes. The Mariner missions in the early 1960s conducted flybys that provided our first close-up data about Venus. Pioneer Venus, in 1978, placed an orbiter around the planet and dropped multiple probes into the atmosphere, gathering detailed information about atmospheric composition, structure, and circulation. The Magellan spacecraft, launched in 1989, revolutionized our understanding of Venus's surface. Using advanced radar that could penetrate the clouds, Magellan mapped 98% of the planet's surface at high resolution. The images revealed a world of incredible geological diversity, despite the uniform appearance from orbit. We saw vast volcanic plains, towering mountains higher than Everest, rift valleys that would dwarf Earth's Grand Canyon, impact craters both large and small, and those mysterious coronae structures that hint at magma chambers beneath. Magellan's radar maps showed that Venus lacks the clear signs of plate tectonics we see on Earth. There are no subduction zones where one plate slides beneath another, no mid-ocean ridges where new crust forms, no transform faults where plates slide past each other. Instead, Venus's surface displays evidence of volcanic activity on a massive scale, vast lava flows that covered thousands of square miles, volcanic constructs of every size and shape, and tectonic features that suggest the crust moves in ways fundamentally different from Earth. The most recent orbital mission, Venus Express, operated from 2006 to 2014, studying the planet's atmosphere and surface in unprecedented detail. The spacecraft discovered that Venus's south pole has a vortex structure even more organized than the North Pole's, with a double eye configuration that rotates around the pole. It detected variations in sulfur dioxide levels that suggest ongoing volcanic activity. It measured the rate at which Venus's atmosphere is being lost to space. And it found evidence that lightning on Venus is far more common than previously thought, with electrical discharges occurring throughout the cloud layers. Japan's Akatsuki spacecraft, which entered orbit around Venus in 2015 after an initial orbital insertion failure in 2010, has continued to monitor the planet's atmospheric dynamics. Akatsuki has revealed that Venus's atmosphere contains gravity waves, atmospheric oscillations that transfer energy and momentum through the air. These waves appear to be generated by surface topography, as air flows over mountains and creates ripples that propagate upward through the atmosphere, similar to how water flowing over rocks creates ripples downstream. Akatsuki also discovered a stationary wave structure in Venus's atmosphere, a bow-shaped feature that remains fixed over the highlands of Aphrodite Terra, even as the rest of the atmosphere races past at hundreds of miles per hour. This stationary wave provides direct evidence that the surface topography influences atmospheric circulation, despite the thick cloud layer that separates them. The finding has forced scientists to revise their models of how Venus's atmosphere behaves, adding another layer of complexity to an already baffling system. But despite these missions, despite decades of study, Venus remains profoundly mysterious. We have landed on the surface only a handful of times, and those landings were brief, measured in minutes or hours rather than days or years. We have never deployed a long-duration rover to explore Venus's surface the way we have explored Mars. We have never collected a sample and returned it to Earth for detailed analysis. We have never sent a balloon or aircraft to float through the atmosphere and study the clouds up close for extended periods. This is changing. Multiple space agencies and private companies are now developing new Venus missions, recognizing that this planet holds keys to understanding planetary evolution, atmospheric dynamics, and the potential for life beyond Earth. NASA has selected 2 Venus missions for development, Da Vinci and Veritas. Da Vinci will send a probe deep into Venus's atmosphere, analyzing its composition and structure as it descends, before potentially surviving long enough on the surface to capture photographs and analyze the surrounding rock. Veritas will use advanced radar to map the surface in even greater detail than Magellan, looking for evidence of active volcanism and tectonic processes. The European Space Agency is developing Envision, another orbital mission that will study Venus's surface and atmosphere with instruments more advanced than any previously sent to the planet. India is planning Shukrayan, a mission that will study Venus's atmosphere and surface from orbit. Even private companies are proposing Venus missions, recognizing that this planet represents both a scientific frontier and a technological challenge worth tackling. Some of the most ambitious proposals involve aerial platforms, balloons, or aircraft that could float in the more temperate regions of Venus's atmosphere for extended periods. At an altitude of about 50 kilometers above Venus's surface, the temperature drops to around 75 degrees Fahrenheit, and the pressure becomes similar to Earth's surface. This is the most Earth-like environment in the solar system outside of Earth itself. A balloon at this altitude could drift with the fast-moving winds, circling the planet every 4 days, studying the cloud chemistry, searching for signs of life, and monitoring atmospheric dynamics. Such a mission could potentially stay aloft for months or even years, far longer than any surface probe could survive. It could carry instruments to sample the clouds directly, analyzing the sulfuric acid droplets for chemical signatures of biological activity. It could deploy smaller probes that descend to lower altitudes or rise to higher ones, creating a 3-dimensional picture of the atmosphere's structure. And it could serve as a communications relay for surface probes, extending their operational lifetime by allowing them to transmit data to the balloon rather than directly to Earth. The concept of human exploration of Venus might seem absurd given the planet's hostility, but some visionaries have proposed exactly that. Not landing on the surface, which would be suicidal, but establishing floating habitats in the upper atmosphere, where conditions are benign. These cloud cities would float at the altitude where temperature and pressure are comfortable, surrounded by a toxic atmosphere, but protected by strong materials and life support systems. The thick atmosphere would provide excellent radiation shielding, better than Mars or the Moon. Solar power would be abundant, and breathable air, being less dense than carbon dioxide, would provide natural lift, meaning a habitat filled with Earth normal air would float in Venus's atmosphere without needing any additional lifting gas. Such habitats could be way stations for exploring Venus's atmosphere, platforms for scientific research, or even the foundation for eventual colonization. The challenges are immense, certainly. The sulfuric acid in the clouds would corrode any material exposed to it, requiring constant maintenance or exotic materials. The fast rotation of the atmosphere would mean habitats would circle the planet every few days, experiencing constant motion. And any failure of the habitat's envelope would be catastrophic, exposing inhabitants to an atmosphere that is both poisonous and corrosive. Yet from a purely engineering standpoint, floating cities on Venus may be more achievable than surface bases on Mars or the Moon. The temperature and pressure are right, eliminating the need for heavy insulation or pressure suits. The atmosphere provides protection from radiation and micrometeoroids. And Venus is closer to Earth than Mars, making travel times shorter and rescue missions more feasible. The idea remains speculative, relegated to the realm of thought experiments and far future possibilities, but it illustrates how our perspective on Venus is evolving from a hellish wasteland to be avoided into a scientific treasure, to be studied, and perhaps even a frontier to be explored. The study of Venus also intersects with one of humanity's most urgent concerns: climate change. Venus represents a worst-case scenario for greenhouse warming, a planet where positive feedback loops spiraled out of control and transformed a potentially habitable world into an oven. Understanding exactly how this happened, what triggered the runaway greenhouse effect, and whether any tipping points exist that could push Earth toward a similar fate, is critical for our own future. Scientists use Venus as a test case for climate models. If we can build models that accurately predict Venus's current state based on what we know about its past, then we can have more confidence in those same models when applied to Earth's future. Conversely, if our models cannot explain Venus, then they are incomplete and may be missing processes that could be relevant to Earth as well. One key difference between Earth and Venus is the carbon cycle. On Earth, carbon dioxide is removed from the atmosphere through a process involving water, weathering of rocks, and the formation of carbonate minerals, like limestone. Rain absorbs carbon dioxide from the air, forming weak carbonic acid. This acid weathers rocks, dissolving minerals that contain calcium and other elements. Rivers carry these dissolved minerals to the ocean, where marine organisms use them to build shells and skeletons made of calcium carbonate. When these organisms die, their shells accumulate on the ocean floor, eventually forming limestone rock. This process locks carbon away for millions of years, preventing it from accumulating in the atmosphere. Plate tectonics completes the cycle. The limestone is eventually subducted into Earth's mantle at collision zones between tectonic plates. Deep underground, heat and pressure break down the limestone, releasing the carbon dioxide back into the mantle. Volcanoes then bring this carbon dioxide back to the surface, releasing it into the atmosphere and starting the cycle over again. This cycle acts as a thermostat for Earth's climate. If the planet warms, more rain falls, weathering accelerates, and more carbon dioxide is removed from the atmosphere, causing cooling. If the planet cools, less rain falls, weathering slows, volcanic emissions accumulate in the atmosphere, and warming occurs. This negative feedback loop has helped keep Earth's climate relatively stable for billions of years, despite the sun growing brighter over time. Venus lacks this cycle. Without liquid water, weathering cannot remove carbon dioxide from the atmosphere efficiently. Without plate tectonics, or at least without Earth-style plate tectonics, there is no mechanism to subduct carbonate rocks into the interior. Carbon dioxide from volcanic eruptions accumulates in the atmosphere with no removal mechanism. The greenhouse effect intensifies, temperature rises, and any water that might have existed evaporates and is lost to space, ensuring the cycle never restarts. This difference highlights how fragile planetary habitability can be. Earth's carbon cycle depends on liquid water, which depends on the planet being at the right distance from the sun and having the right atmospheric composition, which depends on the carbon cycle removing excess carbon dioxide. It is a delicate balance, and Venus shows what happens when that balance breaks. Current human activity is releasing carbon dioxide into Earth's atmosphere at rates far faster than the natural carbon cycle can remove it. We are, in essence, conducting an experiment to see how much we can perturb Earth's climate system before triggering feedbacks that could push the planet toward a new equilibrium. Venus stands as a reminder of how dramatically planetary climates can change, how a world superficially similar to Earth can transform into something utterly alien. Of course, Earth will not become Venus. We are too far from the sun, and the amount of carbon dioxide we could release is far less than what Venus's atmosphere contains. But we could trigger changes severe enough to make large portions of Earth uninhabitable, to disrupt ecosystems that billions of people depend on, and to set in motion processes that would take thousands or millions of years to reverse. Venus teaches us that planets are dynamic systems where small changes can cascade into transformations that are difficult or impossible to undo. Beyond climate science, Venus challenges our understanding of what makes a planet habitable. We once thought habitability was primarily about being in the habitable zone, that region around a star where temperatures allow liquid water on a planet's surface. Venus sits at the inner edge of our solar system's habitable zone, yet it is anything but habitable. Mars sits at the outer edge, and it too is uninhabitable in its current state, though it may have been more hospitable in the past. This suggests that being in the habitable zone is necessary but not sufficient for habitability. Other factors matter just as much or more. The presence of a magnetic field to shield the atmosphere from stellar wind, the existence of plate tectonics to regulate atmospheric chemistry, the initial water content of the planet, the timing and magnitude of volcanic activity, the planet's rotation rate, the composition of the atmosphere, the presence or absence of a large moon to stabilize axial tilt. All these factors and more determine whether a planet in the habitable zone actually develops and maintains habitable conditions. As we search for life beyond our solar system, studying thousands of exoplanets orbiting distant stars, Venus provides crucial context. When we detect a rocky planet orbiting in the habitable zone of a sun-like star, we cannot assume it is Earth-like. It might be Venus-like instead. Distinguishing between these possibilities requires detailed observations of the planet's atmosphere, searching for biosignatures like oxygen and methane that would indicate life, or warning signs like massive carbon dioxide atmospheres that would indicate runaway greenhouse conditions. Some scientists argue that Venus-like planets may actually be more common than Earth-like planets. The processes that make Venus hostile, accumulation of atmospheric carbon dioxide, and loss of water, could easily occur on many worlds. The processes that keep Earth habitable, the carbon cycle and plate tectonics, and magnetic field require a specific set of conditions that might be relatively rare. If so, then truly habitable planets could be uncommon in the galaxy, scattered islands of life in a cosmos dominated by sterile worlds. Others counter that life itself might make planets habitable. On Earth, photosynthetic organisms produce oxygen that reacts with and removes greenhouse gases. Forests and other vegetation accelerate weathering by breaking down rocks with their roots and creating acids that dissolve minerals. Marine life builds vast deposits of carbonate rock that lock carbon away. In these ways and others, life on Earth actively maintains the conditions that allow life to persist. Perhaps any planet where life gains a foothold will be transformed by that life into a more habitable state, creating a feedback loop where life makes the planet more suitable for life. This hypothesis, sometimes called the Gaia hypothesis after the Greek goddess of Earth, suggests that Earth's habitability is not merely a fortunate accident, but an emergent property of life itself. If true, then the key question is not whether a planet is in the habitable zone, but whether life can arise there before conditions become too extreme. Once life exists, it might be able to engineer its own persistence. Venus, in this framework, represents a planet where life either never arose or failed to establish itself before conditions deteriorated beyond recovery. If Venus once had oceans and a temperate climate, did life emerge in those ancient seas? If so, what happened to it when the runaway greenhouse began? Could some organisms have adapted, retreating to the clouds as the surface became uninhabitable, becoming the aerial microbes that might produce the phosphine we detect today? Or did life on Venus go extinct entirely, unable to adapt quickly enough to the changing conditions? These questions may seem speculative, but they are testable with the right missions. A sample return mission from Venus's atmosphere could collect cloud droplets and analyze them for biological molecules, for cellular structures, for any sign of organized complexity that could not arise through chemistry alone. Such a mission is technically challenging, requiring a spacecraft to rendezvous with a balloon or aircraft in Venus's atmosphere, collect samples, and then escape the planet's gravity well to return to Earth. But it is not impossible, and the potential payoff, discovering extraterrestrial life in our own solar system, would be worth the effort. Some of Venus's most perplexing features emerge from studying how the planet interacts with the solar wind. Without a global magnetic field, Venus is exposed directly to the stream of charged particles flowing from the Sunday. These particles interact with the upper atmosphere, creating an induced magnetosphere, a magnetic field generated by electrical currents in the ionosphere, rather than a dynamo in the core. This induced magnetosphere has a complex structure that varies depending on solar activity. During periods of high solar wind pressure, the magnetosphere compresses, bringing the solar wind closer to the planet and increasing atmospheric loss. During quiet periods, it expands, providing more protection. The magnetosphere also develops a long tail on the night side of Venus, where the solar wind stretches magnetic field lines away from the planet. Within this tail, scientists have detected bursts of energetic particles and magnetic field disturbances called flux ropes. These are twisted bundles of magnetic field lines that can transfer energy and momentum from the solar wind to Venus's atmosphere. The process is dynamic and chaotic, with flux ropes forming, detaching, and flowing away in the solar wind. Understanding this interaction is important not just for Venus, but for any planet lacking a strong magnetic field, including Mars and many exoplanets. The solar wind interaction also creates auroras on Venus, though very different from Earth's auroras. Venus's auroras are not visible light displays, but rather glows in ultraviolet wavelengths, created when solar wind particles strike the night-side atmosphere. These auroras are diffuse and chaotic, lacking the organized structure of Earth's auroral ovals. They provide evidence of how energy from the sun is deposited into Venus's atmosphere, driving some of the circulation patterns we observe. Recent studies have also revealed that Venus's induced magnetosphere can sometimes completely collapse during extreme solar wind events. When this happens, the solar wind directly impacts the upper atmosphere, stripping away particles at accelerated rates. These events, though relatively rare, may contribute significantly to the long-term loss of Venus's atmosphere. Over billions of years, countless such events could have removed a substantial portion of the planet's original atmosphere and water. The mystery of Venus's rotation continues to deepen with new observations. Recent measurements suggest that Venus's rotation rate is not constant, but varies slightly over time. The length of a Venusian day appears to fluctuate by up to 20 minutes, depending on when it is measured. This is extraordinary. Planets should not change their rotation rate on human timescales. Yet Venus apparently does. The most likely explanation involves coupling between the solid planet and the massive atmosphere. As the atmosphere circulates, it exerts torque on the surface through friction and pressure differences. This torque can very slightly speed up or slow down the planet's rotation. The effect is small, but Venus rotates so slowly that even small torques can produce measurable changes over months or years. This discovery implies that Venus's atmosphere and solid planet form a closely coupled system, more so than any other planet in our solar system. Earth's atmosphere also exerts torque on the planet, but Earth rotates so much faster that the effect is negligible. On Venus, the atmosphere plays a dominant role in determining the rotation rate. a unique situation that challenges our models of planetary dynamics. Venus also hosts atmospheric phenomena that we struggle to explain. The planet experiences what scientists call superwinds, regions where wind speeds suddenly increase far beyond what models predict. These superwinds appear to be localized, occurring in specific regions rather than globally. And they vary over time. What drives them? How do they maintain such high speeds? And why do they occur where they do? The answers remain uncertain. Another puzzle involves the temperature distribution in Venus's atmosphere. Logic suggests that the day side, facing the sun, should be significantly hotter than the night side, but measurements show only a small temperature difference between day and night at most altitudes. Somehow, Venus's atmosphere efficiently redistributes heat from the day side to the night side, preventing large temperature gradients from developing. This redistribution requires substantial circulation and energy transport, but the mechanisms involved are not fully understood. The clouds themselves present endless puzzles. They form distinct layers at different altitudes, each with different compositions and properties. The lower cloud layer, between 30 and 50 kilometers altitude, consists primarily of large droplets of sulfuric acid. The middle layer, between 50 and 60 kilometers, has smaller droplets. The upper layer, above 60 kilometers, contains particles of unknown composition that may include sulfur compounds or even salts. Above the clouds, a haze extends to around 70 kilometers, composed of submicroscopic particles that scatter light and create the featureless appearance we see from Earth. These layers are not static but dynamic, with droplets forming, growing, falling, and evaporating in a complex cycle. Sulfuric acid is produced by chemical reactions between sulfur dioxide and water in the presence of sunlight. The acid condenses into droplets that grow and fall. As they fall into the hotter lower atmosphere, they evaporate, releasing sulfur dioxide and water vapor that rise back up to form new droplets. This cycle creates a kind of weather on Venus, though nothing like Earth's weather. There is no rain reaching the surface, no storms in the conventional sense, just the endless cycling of acids through the cloud layers. Within these clouds, we have detected what appear to be dark patches that absorb ultraviolet light. These patches, called unknown UV absorbers, have been observed for decades, but never identified. They could be sulfur compounds, they could be iron chloride, they could be some exotic chemical we have not yet identified, or they could potentially be related to microbial life, if the phosphine detection and biosignature hypotheses are correct. Without sampling the clouds directly and analyzing their composition in detail, we cannot know for certain. The presence of lightning in Venus's atmosphere adds another layer of complexity. Lightning requires charge separation, where positive and negative charges become concentrated in different regions, and a mechanism for discharge when the electric field becomes strong enough. On Earth, lightning is primarily associated with water clouds and precipitation. Venus has no water clouds, yet lightning appears to occur, perhaps generated by friction between sulfuric acid droplets or by chemical processes that create charge imbalances. Some scientists have proposed that Venus's lightning could play a role in atmospheric chemistry, breaking apart molecules and creating reactive species that participate in complex chemical reactions. This could help explain some of the chemical anomalies we observe, including potentially the phosphine if lightning can create pathways for its formation that do not involve biology. Venus's surface, despite being hidden from view and hostile to exploration, reveals clues about the planet's past through careful analysis of the radar maps we have obtained. The distribution of craters provides a record of impacts over the past several hundred million years. The craters are surprisingly evenly distributed across the planet, not clustered in old regions the way they are on Mars or the Moon. This even distribution supports the idea that the entire surface was resurfaced at roughly the same time, erasing all older craters and providing a fresh canvas. But not all scientists agree with this interpretation. Some argue that Venus might have a more complex resurfacing history, with different regions renewed at different times in a patchwork process, rather than a single global event. Resolving this debate requires better age dating techniques than we currently possess. Ideally, We would collect rock samples from multiple locations on Venus and analyze them in laboratories on Earth to determine their precise ages. Such a mission remains beyond our current capabilities, but represents a goal for future exploration. The volcanic features on Venus display a diversity that suggests complex magma chemistry and eruption styles. We see shield volcanoes built by low-viscosity lava flowing steadily for long periods, similar to Hawaii's volcanoes. We see stratovolcanoes built by explosive eruptions, though how explosive volcanism occurs in Venus's high-pressure atmosphere remains unclear. We see vast lava channels that transported molten rock across hundreds of miles of surface. And we see features unlike anything on Earth, structures that hint at volcanic processes unique to Venus. The coronae, those circular features hundreds of miles across, appear to be places where mantle plumes, columns of hot rock rising from deep within the planet, pushed up the crust without breaking through. The crust domed upward, creating a circular ridge, and magma may have intruded beneath the surface or erupted around the edges. Some coronae show evidence of later volcanic activity in their centers, or concentric volcanic structures, that suggest multiple episodes of magma intrusion. Pancake domes, another unusual Venusian feature, are circular volcanic structures that look like pancakes, flat-topped and symmetrical. They appear to have formed from very viscous lava that erupted and spread into circular pools before solidifying. The lava must have been viscous enough to hold its shape rather than flowing away, suggesting a composition different from the basaltic lava that dominates most of Venus's surface. Arachnoids, features that resemble spider webs with a central volcanic vent and radiating fractures, are another mystery. They suggest volcanic activity combined with tectonic fracturing, but the exact processes that create them are debated. And tesserae, regions of highly deformed terrain with complex intersecting ridges and valleys, appear to be the oldest parts of Venus's surface, elevated plateaus that somehow survived the global resurfacing event. These tesserae are particularly intriguing because they might record Venus's earlier history. If they are indeed older than the rest of the surface, they could contain clues about what Venus was like before the resurfacing, perhaps when the planet had water and a more Earth-like climate. Future missions that could study the tesserae in detail, measuring their composition and analyzing their structure, might unlock secrets about Venus's past. As we look to the future of Venus exploration, the scientific community is converging on a consensus that we need multiple missions, each addressing different aspects of this complex world. We need long-duration surface probes that can survive for days or weeks rather than hours, giving us time to conduct detailed experiments and analyze the local environment. We need aerial platforms that can study the clouds up close for months or years. We need sample return missions that can bring pieces of Venus back to Earth for analysis in our best laboratories. And we need orbital missions with increasingly sophisticated instruments to map the surface, monitor atmospheric changes, and search for active volcanism. The technology for long-duration surface missions is advancing. New high-temperature electronics, built from silicon carbide or other materials that remain functional at Venus's surface temperatures, could allow instruments to operate without refrigeration. Heat-resistant materials could protect critical components. And innovative designs, like a mechanical rover that uses springs and levers rather than electronic motors, could function in conditions that would destroy conventional robots. For atmospheric exploration, advances in balloon and aircraft technology make extended missions increasingly feasible. Solar-powered aircraft could fly continuously at high altitude, above the thickest clouds, using solar energy during the day and stored power at night. Balloons made from resistant materials could drift through the cloud layers, ascending and descending to sample different altitudes, potentially staying aloft for years while circling the planet dozens or hundreds of times. Sample return from Venus presents unique challenges, but is not impossible. A mission would need to collect surface samples, or atmospheric samples, launch them off the planet despite the thick atmosphere and high gravity, and then return them to Earth. The engineering is daunting, but feasible with modern technology. The scientific payoff would be immense, allowing us to analyze Venus material with instruments far more sophisticated than any we could send to the planet. Venus stands as one of the great challenges in planetary science, a world that defies easy explanation, that reveals new mysteries as fast as we solve old ones. It is a planet that forces us to question our assumptions about how worlds work, that reminds us that the universe is stranger and more diverse than our theories predict. Every mission to Venus, every new observation, every puzzling data point, contributes to our slowly growing understanding of this enigmatic world. But perhaps the deepest lesson Venus teaches is humility. We live on a planet that is habitable through what appears to be a delicate balance of factors, many of which we still do not fully understand. Venus, our nearest neighbor, our sister world, shows how easily that balance can be lost. It reminds us that Earth's habitability is not guaranteed, not permanent, not invulnerable to disruption. As we gaze at Venus in our evening sky, that brilliant point of light that has captivated humanity since before recorded history, we are looking at a world that might have been like Earth, that perhaps once had oceans and temperate climates, that may have even harbored life. We are looking at a planetary cautionary tale, a world transformed by processes we are only beginning to comprehend. And we are looking at a frontier, a place of mysteries waiting to be solved, of questions waiting to be answered, of knowledge waiting to be gained. Venus is seriously off, yes, but in being so, it may have more to teach us about planets, about climate, about habitability, about the cosmos itself than we ever imagined. The images we have captured, showing a world of extremes, of backwards rotation, of crushing pressure and searing heat, of acid clouds and super-rotating atmosphere, reveal not just a planet, but a puzzle. And like all the best puzzles, solving it will require ingenuity, persistence, and a willingness to challenge everything we thought we knew. The exploration of Venus has only just begun. The missions launching in the coming years will revolutionize our understanding. They will answer questions we have pondered for decades, and raise new questions we have not yet thought to ask. They may even discover life, or at least the remnants of life, in the clouds of this hellish yet fascinating world. And as we explore Venus, we explore ourselves, our own planet's past and future, our place in the cosmos. For in understanding how Venus became what it is, we gain insight into how Earth became what it is, and how we might keep it that way. In studying a planet where everything went wrong, we learn how to keep things going right. In facing the mysteries of Venus, we confront the limits of our knowledge and the vastness of what we have yet to learn. This is the gift Venus offers us, wrapped in extremes and mysteries, hidden behind impenetrable clouds. A gift of knowledge, of perspective, of humility, and of inspiration. A reminder that the universe is endlessly complex, that worlds can differ in ways we struggle to imagine, and that the quest to understand our cosmic neighborhood is one of the great adventures of human civilization. Venus, the evening star, the morning star, goddess of beauty, concealing a heart of fire, a planet seriously off, and all the more valuable for it.